I want to talk about some really neat applications of the right-hand rule and magnetic forces. Now, here's the first one. Consider an electron as follows. Wait a minute. Does our right-hand rule work for negative charges? No. Eric, what direction is this electron traveling? To the? So that's the same as a proton traveling to the? Everybody point your right thumbs to the left. What direction is the magnetic field? Into the, which way will this electron get deflected? Now, here's what's going to happen. Right when it hits the magnetic field, it's going to start to deflect down. But now the electron is traveling down and right. That's the same as a proton traveling up and left. Point your thumbs up and left. What direction will the deflection occur? Kind of this way. Okay, so now it's going to get deflected this way. Now it's moving straight down for a split second. That's the same as a proton traveling straight up for a split second. It's going to get deflected this way. In fact, what the electron is going to do, if I do a better picture, is this. The electron is going to be forced into a circle. This is why particle accelerators are circular. You're using magnets to deflect particles in a magnetic field. In fact, you know what this means that we can say? Unlike for gravity, where we used to say gravity is what's pulling us in a circle for orbits, we can say magnetic force is what's pulling us in a circle. Ashley, what's my equation for magnetic force on a moving charge? Not on a wire, on a moving charge. From your formula sheet, which by now I'm sure you have out in front of you. Did I pick on you because I noticed you didn't have the formula sheet out earlier? Did I save it for now? Yes. What's our equation for the magnetic force on a moving charge? One of the ones we did yesterday. Sorry? Is it Bill? Is Bill, wait a minute, charge. What's our symbol for a charge? What letter? Q, the one with the Q in it, please. We're going to get this. QVB equals mv squared over r. Or QVB equals m4 pi squared r over t squared, but I'm never going to ask you for the period. I'm going to ask you for the speed or the radius. In this specific equation, I notice there's a v for speed on the left, there's a v for speed on the right. Are they going to cancel, or are we going to get a v cubed? Kyle. Yeah, what I could do is I could go divide by v, divide by v. In fact, really, this simplifies to QB equals mv over r. But it starts out as magnetic force is what's pushing me in a circle. How many variables are there in this equation? 1, 2, 3, 4, 5. As far as I'm concerned, I can give you 4. You can find the 5th. And I like, well, you know what? Let's get to example 2. I like this question. I like this question. I like this question. An electron moving at 3.2 times 10 to the 7th meters per second enters a perpendicular magnetic field and traces out a circular path. Okay, I got this. Victor, what does it want me to find? Are we tracing out a circle? Then we can say magnetic force is what's pushing me in a circle. We can say QVB equals, don't forget the m, v squared over r. One of the v's will cancel, Victor. I'll do that right now. What are we trying to find? Where is the r right now? On the... Bleh! Oh, how can I take care of that? Dividing by r on the right is the same as doing what? On the left. I would cross out the r, move it to there. I want to get the r by itself. How will I move the QB over? R is going to be mv over QB. M. It's an electron. Thank you, Victor, for being clever enough to know, hey, it's on my sheet somewhere. It's the 9.11, but I can never remember the 10 to the... V, the speed, 3.2 times 10 to the 7th, all over. Q, it's an electron. By the way, it's almost always going to either be an electron or a proton. Those are the two most common things that we accelerate in particle accelerators. If it's something else, I'll give you the mass and the charge, but it's almost certainly going to be an electron or a proton. Charge on electron? We'll skip the negative because we don't want a negative radius, so just 1.6 times 10 to the negative 19. You're correct. It is technically negative, but we ignore that. And B, 5.45 times 10 to the negative 4. What do you get? I made this up. I'm hoping you get decent numbers. I hope it's not like a radius in the kilometers or in the micrometers. I hope. All of you should probably practice typing these in. I had a lot of kids make typos this morning in my Block F class. Let me know what you get when you're done, Victor. Doing some really rough math. I think you're going to get something in the 1 decimal place, like point something. What'd you get? Is it 0.33? It gives me the three figs. 0.33, 0.334 meters. About that, right? Because 30.3 meters is a centimeter, is 30 centimeters is a ruler. So a little bigger than a ruler. I was hoping for something that would be you could see and detect. Where this is really used, by the way, is for unknown particles. You send them through a particle accelerator, you photo their radius, you can watch it on camera. If you know R, you can either solve for the particle's mass or its speed or its charge. This is how we can figure out what unknown particles are. I like example 3, I like example 3, I like example 3. From January 1990, this was a 7-mark question on the provincial exam. As shown on the above diagram, a proton entered a magnetic field at A. The radius R was measured at 3.25 meters when the magnetic field strength was 2 times 10 to the negative 2 teslas. What was the proton's speed when it entered the magnetic field at A? Huh, good question. Okay. Kyle, what's this asking me to find? Are we moving in a circle? Magnetic force is what's pushing me in a circle. If you want to, you can skip straight to QVB equals mv squared over r, but this is our thought process. Oh, a v cancels this time? What are we trying to find? Get the v by itself. Read me my new equation. What does v equal? What over what? Q B R over M. Yeah. Q, it's a proton. B. They said 2 times 10 to the negative 2, Kyle. I'm going to write 0.02 because that's less writing, and that's the same value. R, 3.25. M, it's a proton. It's a proton. Yeah. Would I have the 9.11 if this was multiple choice as an answer to pick from? Maybe. What 1.67? I always forget the 10 to the times 10 to the negative 27. Okay. There is a bit of a built-in error check in that it can't be traveling faster than the speed of light. So I know you're going to get an answer less than 3 times 10 to the 8th, but you're going to get a pretty big answer. These subatomic particles, we can get them going pretty fast. Let me know what you get. .23 times 10 to the 15? No, that's faster than the speed of light. That has to be impossible. Here is my guess. Check your negatives and your positives for your exponents. Because I think it is a 623, yes? So check your 10 to this. There's got to be a typo on your calculator in your 10 to this. I think, isn't it 6.23 times 10 to the sixth? I don't know if you remember yesterday, we solved for an acceleration. It was like 10 to the 13th or something, and I went on a rant about, wouldn't you go faster? No, no, the acceleration is what's bending you in a circle. It's not changing your speed. It's what's causing this proton to move in a very, very rapid circle. So there's going to be some variation of this on your test. I'll give you a moving charge, probably an electron or a proton, moving in a circle, and I'll give you 4 of the 5 things, and I'll ask you to find the 5th one. And this is what I also said yesterday, Fahim. The math in this unit isn't that bad. It's mostly cross-multiplying. The tricky part is the right-hand rule E stuff, and there will be also lots of direction E questions on your test too. So where do we use this? Put your pencils down, look up. Another really cool application, electric motors. This is how we can turn, Dean, magnets and mark as current and combine them to get motion. This is good stuff. Suppose a rigid wire loop is placed in a uniform magnetic field as shown below. It says determine the direction of the current in each segment. Well, I can do that. Kenta, what side of the battery is positive here at the bottom, the left side or the right side? So the current is going to go this way. So I guess in section 1 it's going that way, section 2 it's going up, section 3 it's going right, section 4 it's going down, section 1 is traveling left. Draw those in. And then, Kenta, it asks for the direction of the force on each segment. Kenta, look at line 3, section 3. Is it parallel or perpendicular to the magnetic field? What's the magnetic force when you're running parallel to the magnetic field? Do you remember? 0. Okay? No force from 3. So if we scooch down here, none for section 3. By the way, same for section 1. No force for section 1 because it's also running parallel. There will be a force, Kate, on section 2 and section 4. Let's look at section 2. Kate, what direction is the current moving in section 2? What direction is magnetic field? Time for your right-hand rule. Section 2 is either going to get pushed into the page or out of the page. Which way is section 2 going to get pushed? Okay, so section 2 into the plane of page. What about section 4? Emily, out of the page. And so what's going to happen, if we have an axle running along the middle right here, it'll spin. Unfortunately, though, it'll only spin a half turn because as soon as section 4 gets to the left-hand side, it's also going to feel a force which way? Into the page. But the current itself, like if we spin this whole thing, as soon as section 4 gets to this side, now the current will be moving downwards. It's going to want to get to forced up. It would wiggle back and forth, but we would like to come up with a way to get this to spin, like spinning a wheel. So here is our clever solution. This, Fahim, is that okay? Aryan, that okay? This is important. You got to be wrapping your brain around the right-hand rule stuff. So it says figure 7.28 shows a simple one-turn coil. I didn't realize the picture's on the next page. However, I would like you to underline the word armature. The thing that spins inside of an electric motor, we call that the armature. I'm not going to test you on that, but I'm going to use that term vocabulary in questions. So, turn the page. This is how an electric motor works. So this is a very simple electric motor, a single turn of wire. If you want to make the motor spin faster, you have multiple turns of wire, or better yet, instead of turning a wire, turn a solenoid. But here's our start. Current is moving up the page over here. Which way do magnetic field lines point from what to what? North to south. The left side of this armature what direction will it feel a force? Will it get pushed upwards or will it get pushed downwards? Use your right hand rule and figure it out. Eric. Downwards. So the left-hand side is going to get pushed downwards. Here's an end view. The right-hand side is going to get pushed upwards, and it's going to start to spin. But the problem is, once it's spun halfway, then I would have the current moving down on the left, and that would mean it would get forced up. It would just go back and forth. So here's what we do. We have something called a split ring commutator. Think like a hamburger with no patty. And what we have then is this is actually closed off. There's a hollow gap in the middle, and we have metal brushes that are just touching this. And what you get is this effect here. Put your pencil down, look up. Here is a good visual of a DC electric motor. In the middle here is the split ring commutator. See the gap? So right now, at the very beginning, I have current flowing this way, this way, this way. You know what? I'm feeling a force down in the top. I'm feeling a force up in the left. Right here, for a split second, there's no current flowing. That's what that gap is doing. There's no current flowing, but the momentum of the motor will keep it spinning. This is a clever way to take a direct current from a battery and somehow make it alternate so that you always get the current going in the same direction on the right side, and you always get the current going in the same direction on the left side. You let its own momentum just carry it. I got a better version of that. Okay, so here's kind of a 3D version. Again, there's the split ring commutator right there for a split second. No current is flowing in the armature. There's no force, but its momentum is keeping it going. This is a clever way where I can guarantee that the current is always flowing which way? To the right in the top and coming out of the page, or to the left on the bottom, so that the force is always that way on the bottom and is always that way on the top. Now, there's a problem with this method. The problem is if you shut the motor off and it comes to a stop right like that, it won't start up again when you start it. So modern motors have 3 armatures in kind of an equilateral triangle, and that way, no matter where it stops, there will always be a net force when you turn the switch back on. Okay. One more. What was it called, Mr. Dueck? I don't remember. Magnetic forces, this one here.
The torque in a DC electric motor is created by magnetic forces exerted on
Right there, no force.
the electric current carried by the rotating part
Right there is the maximum force
of the motor. In this virtual model, the flow of conventional current is represented by the moving red balls. The magnetic field is represented by the blue lines. The current loop experiences a torque due to the offset forces on the top and bottom sections of the loop. The forces on the front and back segments of the loop exactly cancel, so they do not contribute to the net torque on the loop. The battery that drives this motor produces a constant voltage which can only drive the current in one direction. However, the motor loop would get stuck lined up perpendicular to the magnetic field if its current never changed direction. A clever mechanical connection called a commutator allows the single direction battery to supply a current to the loop that switches direction every half rotation.
And I have a couple of these. Let me pause the video and bump up the lights. So here's a side view of a solenoid one. I'm not going to test you on the solenoid versions. They're a little more complicated, but you can read through. Really, the key idea is, hey, electric motors come in all sizes. Some are very tiny. They drive toys. Some are huge, drive trains. You'll find them in toy trains, automobiles, clocks, wheelchairs, streetcars, can openers. I mean, any type of rotating electric tool There's an electric motor. Your phones, that's what makes your phones vibrate. There's a solenoid in there, and there's an electric motor spinning, probably with one of the weights offset slightly, so that's how you get the little vibration effect. Okay. What's your homework? Can you cross out number 9, please? Your homework is really the take-home quiz, but you can try 13, 14, 15, and 17. But can you all get out the ultimate review, please? We need to cross out some questions from the ultimate review. Pause for a second. Cross out, and these ones you can cross out because I haven't covered this. Number 2, this is how TVs, the old style of TVs used to work. They had solenoids and deflecting magnetic fields. Really cool, but I'm skipping that. So you can cross out number 2. Cross out number 4. Cross out number 8. You can cross out number 16, 1, 6. You can cross out number, there's another one coming up, I know, 31. 34. And all of the scholarship questions.